Barry throws a ball off a cliff with an initial speed of 11.4 meters per second and an angle of 15 degrees below the horizontal. The ball falls a vertical distance of 15.5 meters into a lake below. How much time does the ball spend in the air? And B, that's A, and then B, what is the velocity of the ball just before it strikes the water? All right, so let's draw a diagram. Here we've got a cliff and the lake below. The ball now is being thrown at 11.4 meters per second, but at 15 degrees below the horizontal. So the ball is being thrown downwards like that. 11.4 meters per second at 15 degrees below the horizontal. So what's the motion going to look like qualitatively? In this case, it's going to come down like that. Okay, and go in the water there. The height of the cliff is 15.5 meters, so it's 15.5 meters above, like that. There we go. And then how much time does the ball spend in the air, and what is the velocity of the ball just before it strikes the water? So let's write down the coordinate system. Let's again pick our coordinate system down here at the lowest point, most to the left. So at the ground level, or the lake level, I guess we should say, below the initial point of the ball, what are the variables? X naught, X, V naught, X, Vx, Ax, Y naught, Y, V naught, Y, Vy, Ay, and T. X naught, what is the initial X coordinate? 0. Y naught, in this case, 15.5 meters. X, we don't know that, and actually we're not looking for that this time. Y, coming down to the lake, so the final height is 0. V naught X, V naught Y, we're going to have to solve, again, the triangle here. So let me move the problem. Let's remember, what are we looking for? Let's just jump up around a little bit. What are we looking for? We're looking for how much time, so we're looking for T. But then we're looking for what's the velocity of the ball. So we need to find, in order to describe the final velocity, we need to describe Vx and Vy, and then put them together to determine what is the final velocity vector. So we're looking for the final velocity, we need the components to find that. So we need to find Vx, and we need to find Vy, and then we'll put them together. Okay, let me move the problem and give us a little more space. In order to determine V naught X and V naught Y, we're going to draw our diagram here. Here's our initial velocity, which is now 15 degrees below the horizontal. This side will be V naught X, this side V naught Y. So what do we have? V naught X will be 11.4 cos 15, which turns out to be 11.0 meters per second. But V naught Y, notice V naught Y is downward. The initial Y component is downward, which means the Y component is going to be negative. This is a very, very important difference between this problem and the other problems. Here, our initial velocity, which is below the horizontal, means the initial Y component has to be 0. So we get a negative 11.4 meters per second sine 15, which gives us a negative 2.95 meters per second. Then calculating T, again, not enough information in X to do it. From Y, we solve Y equals Y naught plus V naught YT plus 1/2 AY T squared. Putting in the values like we always have, solving the quadratic, we end up with negative 0.30 seconds plus or minus 17.7. Now, let's look at this. What is this? The peak of our motion is at a negative time. Well, that makes sense. Again, drawing this back, this will peak here and then come down. The peak is actually before it was thrown, and so we have a negative time here, then plus or minus this, or negative 18 seconds and positive 17.4. So the time when it would be at the lake level is a larger negative value, a smaller positive value, yeah, because this would take a longer time than this side. So that makes sense. Very good. But which number do we want? We want the 17.4. Putting that in for the final, that's the time. That answers part A. Now, what about the final velocities? This is something that we haven't mentioned before, but is basically going to apply to just about any of these types of problems. What is our final velocity in x? Remember, Vx is v naught x plus axt, but what is ax? Ax, for any of these types of problems, is 0. So this is 0, which means what? Vx is equal to v naught x. Because there is no acceleration in the horizontal direction, our final x velocity component is always going to be the same as our initial x velocity component. We haven't mentioned that before, but from symmetry, that makes sense. Because there is no acceleration horizontally, the velocity horizontally is constant. But for the y component, putting in our y values with our positive time, we come up with a very large y velocity, that should be negative 173 meters per second. It's going downwards very, very fast. All right, let's put these two together, Vx and Vy. We'll put those together and figure out what's the final velocity. We have our final velocity has an x component of 11.0 meters per second, a y component of negative 173 meters per second, so we draw it in the downward direction. And now, just like one of the vector problems in the homework practice problems, we can figure out what v is. V is going to be the square root of a squared plus b squared, or 173 meters per second. It turns out that the 11, this x component is so small that to 3 sig figs it doesn't even change the value. So 173 meters per second. We find the direction, tan of theta is opposite over adjacent. Inverse tan gives us 86.4 degrees. So what's the final velocity? Final velocity, 173 meters per second at an angle of 86.4 degrees below the horizontal. Okay, there we go. Very, very good. We found the time for part A. We found the final velocity for part B. Now, I'm sorry, I know I said this was going to be the last one, but let's do one more because there's one more point that I want to emphasize in solving these problems. Last problem. Now, really the last problem. Jasmine throws a rock at an angle of 15 degrees above the horizontal with a speed of 25 meters per second. A, how high does it go? B, how far does it go? Now, because I'm trying to sneak in one more problem here, I will just do part A. How far does it go? That looks very similar to some things that we've already solved, so we won't do that one. We'll just do part A. Let's draw a picture. So here we've got Jasmine throwing a rock. We are not given an initial height for the rock, so we'll just assume it's at ground level. So she's kind of holding it down here, throwing it at ground level. So 15 degrees at 25, or I should say 25 meters per second at 15 degrees. And the question is, how high does it go? So qualitatively, again, what's this motion going to look like? Well, it's going to go up and then back down. And the question is, how high does it go? So what is it asking? It's asking, what is the height at this maximum point? What is the y value? Well, depending on where we put our origin, what is the height when it's at the maximum point? Okay, let's put down the variables. X naught x, v naught x, vx, ax, y naught y, v naught y, vy, ay, and t. And let's put our origin, well, I was supposed to pick the origin first, wasn't I? Let's pick the origin over here at the initial position of the ball. So we've got x naught is 0, y naught is 0. X, well, this would be x. We don't know what that is. Y, don't know what that is, but that is what we're looking for. V naught x, okay, well, from our triangle, we know V naught x will be 25 cos 15, and that turns out to be 24.1 meters per second. V naught y, that'll be 25 sine 15. Hopefully these are looking familiar enough that I don't need to write it completely out. And that gives us V naught y is 6.47 meters per second. Vx, well, we're not given that, but can we figure out what Vx is? I'll give you a hint. What's Ax? Ax is 0, and if Ax is 0, The velocity in the x direction is constant, so we know that's going to be 24.1 meters per second. What is Vy? Now, this is the important point I wanted us to get to. If you remember back when we were looking at one-dimensional motion, well, a very similar sort of thing happens in two-dimensional motion. When we are tossing something, here we go. When we're tossing something, at the maximum point, what describes the maximum point? It's not when the ball is stationary. That was something that happened when we had one-dimensional motion. In two-dimensional motion, it's still moving. It's still maintaining a horizontal velocity, which is constant throughout the entire motion. But the y motion, the velocity in the y direction, that's what is zero at the peak. So as the ball is moving like this, at the peak, it's still moving horizontally, but it's not moving up and down anymore. So the important idea here is that at the peak, to determine how high it goes, that is where Vy is equal to 0. That's the important idea that I wanted us to get to in this problem. And then Ay is negative 9.80 meters per second squared, and t we don't have. Okay, so how are we going to go about doing this? Well, we actually don't have to solve for t. If we're looking for y, what can we do? We can use, if you remember, the fourth equation in y. So let's do that. I'll move the problem and solve it using the fourth equation. Solving the fourth equation in y, we have Vy squared equals V naught y squared plus 2ay times y minus y naught. But we know Vy is 0 at the peak, and we know y naught is 0, the initial height. So we end up with 0 equals V naught y squared plus 2ay times y. We're looking for y, so let's bring this term over here and then divide by the 2ay, or bring this term over here and divide by 2ay. We end up with negative V naught y squared divided by 2ay equals, now, before we put the numbers in, does that look familiar? Yeah, well, that's the result that we found. What's the height of an object being thrown from ground level, except we had V naught sine 2 theta in there. So we've got V naught y squared, more general case, negative 6.47 meters per second squared divided by 2 times ay, negative 9.80. Notice the negatives cancel, which is always good. You should always make sure to be very careful and keep all the minus signs in as you're going along. And if you're supposed to get a positive number, they should cancel out with each other. And if they don't, you know you've made a mistake somewhere. Dividing this out, what do we get? We get y is equal to 2.14 meters. Does that seem like a reasonable result? Well, it's being thrown at 15 degrees. Now, 15 degrees really is a relatively small angle, and so it's not being thrown at a very steep angle, but a small angle, and the fact that it only gets up 2.14 meters, actually that kind of makes sense. Okay, very, very good. So far, what we've been doing the last few lectures have been kinematic problems. We've been looking at motions, but not explaining why they had the motions they have. We've said they've had a particular acceleration. What we're going to do now is we're going to start looking at the area of physics called dynamics. And to do that, we're going to have to introduce some new ideas, and we'll start with that next time.